Tonight we're going to talk about two machines that are still moving. Right now, as you listen to this, a spacecraft called Voyager 1 is approximately 170 astronomical units from Earth. That number may not mean much yet. It will. What you need to know first is this. If you sent a radio signal to Voyager 1 at this moment, a signal travelling at the speed of light, it would take nearly 24 hours to arrive. Not 24 minutes, 24 hours. And then another 24 for any reply to come back. We launched it in 1977. It is still going. And 2 months ago, engineers at NASA's Jet Propulsion Laboratory had to shut down one of its last remaining science instruments. Not because the instrument broke, not because the mission failed, but because there was no longer enough power to keep it running. The machine that first crossed into interstellar space, that first told us what the universe feels like beyond the sun's reach, is now operating on 2 instruments. 2. Out of the 10 it launched with nearly half a century ago, the horrifying truth about the Voyager journey is not that it might end. It is what the mission has revealed, and what it will become when the last signal fades, and the machine keeps going anyway, silent and permanent, deeper into a dark that does not care that it is there. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. There is a room at NASA's Jet Propulsion Laboratory in Pasadena, California, where engineers have been talking to Voyager 1 for nearly 50 years. The conversation is not easy. It has never been easy, but it has become something else entirely over the decades, something that has no real name in ordinary human experience. Because what happens in that room is not a conversation in any normal sense of the word. It is a series of instructions sent into a silence so deep that the instructions take nearly a full day to arrive, and another full day for any response to return. The engineers at JPL send a command in the morning and the reply comes back 2 days later. They are not talking to Voyager 1 the way you would talk to someone in the next room, or even the way you would talk to someone on another continent. They are talking to something that exists in a different relationship with time than anything else we have ever tried to manage. Think about what that actually means. The signal leaves Earth at the speed of light, which is the fastest that anything in the known universe can move, 300,000 kilometers per second, and still it takes nearly 24 hours to reach Voyager 1. In the first 2 seconds after leaving Earth, the signal has already passed the Moon. In about 3 minutes, it has covered the average distance to Mars. In roughly 45 minutes, it has cleared the distance to Jupiter. And then it keeps going. 4 hours through a region of space that contains almost nothing, where the sun appears as merely a very bright star among other stars, where the nearest planet is so far behind that it has been out of reach for decades. The signal travels through this emptiness for the better part of a day before it finally arrives at Voyager 1, which is approximately 15.5 billion miles from home, moving away from it at 61,000 kilometers per hour. That is where Voyager 1 is right now, not where it was when this script was written, where it is at this moment. The distance updates every second. The spacecraft has not stopped moving since September 5th, 1977, and it has not changed direction. No engine has fired in decades. There is no fuel being consumed, no thrust being applied. It is simply coasting on the momentum it gathered nearly 50 years ago, following the path that physics drew for it, and it will continue following that path long after every person connected to this mission has gone. When engineers at JPL sent the command on April 17th of this year to shut down the low-energy charged particle instrument on Voyager 1, the command left Earth and travelled for 23 hours and 32 minutes before it reached the spacecraft. The instrument had been running almost without interruption since 1977. It measured the fluxes of ions and electrons in the interstellar medium, helping scientists understand the environment that exists beyond the Sun's reach. It had been one of the tools that helped confirm Voyager 1 had crossed into interstellar space more than a decade ago. And now it was off. A small motor inside the instrument was left running. The team is not quite ready to call the shutdown permanent. They have been surprised before by this machine. But the door is mostly closed. Voyager 1 now carries 2 functioning science instruments. One listens to plasma waves moving through the interstellar medium. One measures the magnetic field. They are, according to the mission team, still working well, still returning data from a place no other instrument has ever sampled. But the power supply that keeps them running has been declining at roughly 4 watts per year since the day the spacecraft launched, and the margin between enough and not enough has been narrowing for a long time. The machine is still moving, the machine is still listening, but the machine is running out of time in a way that is slow and measured and permanent, 4 watts at a time year after year, with no remedy available. If an engineer at JPL says good morning to Voyager 1 at 8 o'clock on Monday morning, the message arrives late Tuesday. If Voyager 1 responds, the reply arrives Wednesday morning at 8. The exchange takes 48 hours, and every day the delay grows by a tiny fraction as the spacecraft moves further away from Earth, further from the Sun, further from anything. In November of this year, Voyager 1 will cross a distance of 1 full light day from Earth. That is the distance that light itself travels in 24 hours, roughly 26 billion kilometers. No human-made object has ever been this far from home. At that point, any command sent from Earth will take a full day to arrive, and any reply will take a full day to return. The round trip will span 2 calendar days, and that delay will keep growing for as long as the mission continues, and after the mission ends. For as long as the machine moves, which is to say, forever, think about the people whose job it is to do this. To send commands that take a day to arrive, to receive data that takes a day to return, to make decisions about a machine that exists so far away that the word management barely applies in its ordinary sense. They cannot visit the spacecraft. They cannot inspect it or repair it or replace any component on it. They can calculate where it is, they can estimate what its systems are doing based on the data it sends back, and they can send instructions that will arrive tomorrow. That is the full extent of what the relationship allows. Every watt of power the spacecraft uses is being tracked. Every decision to run one system is a decision to take power from something else. Every instrument shutdown has been permanent. There is no undo. There is no second chance. There is only the slowly declining power budget and the choices made within it, one at a time, over nearly 50 years. This is not a museum piece. This is not a retired mission in storage somewhere. It is moving right now, at this moment, further than it was when you started listening to this, further than it will be when you finish. The distance is a number that only increases, and it will only increase for the rest of time. The people who work on this mission have a particular kind of patience that is different from ordinary patience. Ordinary patience is waiting for something. What the Voyager team practices is something more like sustained attention across enormous timescales. The willingness to maintain a relationship with a machine that replies in days, to make decisions about a system that cannot be inspected, to care about data arriving from a place that will never be visited by any person they know or any person their children will know. There is a specific quality to this that becomes apparent when you look at the numbers. The signal takes nearly 24 hours to arrive. Any response the spacecraft sends takes nearly 24 hours to return. So on any given day, the team is simultaneously sending commands that will arrive tomorrow, receiving data that was measured yesterday, and monitoring a situation that is always at least a full day behind what is actually happening on the spacecraft. They are managing the present moment of a machine by reasoning about its recent past and instructing its immediate future, with no ability to respond in real time to anything. And yet, the mission has operated this way effectively for nearly 50 years. Every instrument shut down, every power conservation decision, every trajectory calculation has been executed correctly from this remote position, under these impossible communication constraints, for a machine that has now travelled farther from Earth than any object humans have ever sent anywhere. The farthest human-made object in the universe is still, in some functional sense, being managed by people sitting in California. The conversation they're having with it is conducted in days, and it is still working. There is a difference between knowing a number and feeling it. 170 astronomical units. The phrase sounds precise. It has a scientific quality that suggests understanding, but knowing the number is not the same as understanding what it means to exist that far from anything familiar. So before we follow Voyager any further into its story, we need to stop here and feel the scale properly. Because everything that follows, the instrument shutdowns, the heliosphere crossing, the golden record drifting through the dark, none of it carries its full weight unless the distance becomes real to you first. Start with something close. The Moon is roughly 384,000 kilometers from Earth. On the Apollo missions, the trip to the Moon took about 3 days. When the astronauts spoke to mission control from the lunar surface, there was a delay of about 1.25 seconds each way. You could hear it in the broadcast footage, that slight pause before the response, that brief moment of waiting. It was noticeable. It was a little strange. But it was manageable. A 3-day trip produces a 1-second communication lag. Mars, at its closest approach to Earth, is about 54 million kilometers away. Signals to Mars rovers take between 3 and 22 minutes to arrive, depending on where the two planets are in their orbits. Mission controllers send commands and wait. The rover acts and reports back, and the report arrives minutes later. Every instruction is a decision made in the past, arriving in the future. Every emergency must be anticipated in advance, because real-time control is impossible. Jupiter, at average distance, is roughly 600 million kilometers from Earth. A signal takes about 33 minutes to arrive. Saturn is further. Uranus is further still. Voyager 1 is not Jupiter far. It is not Saturn far. It is not at the edge of the solar system in the way Neptune is at the edge. It is beyond Neptune by a distance that makes Neptune seem local. It is at 170 times the distance from the Earth to the Sun, which is itself about 150 million kilometers. Try to feel this differently. If you took the solar system and laid it out on a map on your floor, with the Sun as a grapefruit in the center, Earth would be a grain of sand about 1 meter away. Saturn would be at about 10 meters. Neptune, the outermost planet, would be at about 30 meters, and Voyager 1 would be somewhere past the 45-meter mark, outside the room, in the hallway, past the hallway, and still moving away from the grapefruit at speed. The nearest star system, Alpha Centauri, would be roughly 420 kilometers away in this model. Voyager 1 has not reached a fraction of that distance. Make the distance personal. If you drove toward Voyager 1 at highway speed, 100 kilometers per hour, without stopping, The drive would take roughly 17,000 years. Not 17 years, not 1700, 17,000. In that time you would watch human civilization rise and fall multiple times, assuming a car, a road, and breathable air could somehow exist across interstellar space, which they cannot, and assuming you did not need to sleep, which you do. If you walked at a comfortable pace of 5 kilometers per hour, you would not arrive before the sun exhausts its hydrogen and begins to expand. You would be walking when this solar system ends. And here is the part that most people skip over, because the number of the distance sounds large, but what fills it sounds like nothing, and nothing is hard to feel as a quantity. Between Earth and Voyager 1 there is almost nothing. The region of interstellar space that Voyager now travels through contains roughly 1 hydrogen atom per 5 cubic centimeters, on average. The air you are breathing right now contains something like 27 billion molecules per cubic centimeter. The space around Voyager 1 is the opposite of that, in a way that ordinary experience provides no frame of reference for. It is the closest thing to true emptiness that the physical universe offers. There are no planets out there, no asteroids, no comets in that region, no dust clouds you could see against the stars, no waypoints, no markers, no structure of any kind that would look familiar to a human eye, just the thin cold of interstellar space and ancient cosmic rays travelling at near light speed, and the background magnetic field of the galaxy, doing things on timescales that our language was not built to contain. And in the middle of all of that, one small machine, roughly the size of a compact car, carrying instruments that were built in the 1970s, moving steadily and silently in one direction at 61,000 kilometers per hour. The distance is not impressive in the ordinary way that word implies something you can admire from the outside. This is a scale that does something else. It swallows everything, including the admiration. The universe is mostly this: emptiness between things, vast regions of almost nothing connecting the very occasional something, and Voyager 1 is now fully inside it in a way that no other human artifact has ever been. In November of this year, the signal delay will cross 24 hours. A full light day. Any message sent from Earth will arrive tomorrow. Any reply will come back the day after that. The conversation between a civilization and the farthest thing it has ever sent will be conducted in days. And the distance will keep growing. Every hour, every minute, every second of the rest of time, Voyager 1 will be a little further away than it was. There is nothing out there to stop it. There is nothing to slow it. There is nothing to pull it back. It will continue in this direction, at this speed, effectively forever. To understand how a machine arrived at this place, you need to go back to a specific year and a specific alignment of the sky that opened a window that would not stay open long. There is also the question of what that emptiness actually feels like in human terms, as opposed to physical terms. Human beings have never experienced genuine isolation. Even the loneliest places on Earth are still Earth. There is air, there is sky, there is gravity that matches our bodies. There is weather and temperature and a horizon and a star that rises every morning to mark the passage of time. A person standing alone in the middle of the Sahara Desert is still in a comprehensible place, still under the same sun that has risen and set for their entire life. The region of space Voyager 1 now occupies is not comprehensible in any of those terms. The sun appears as a bright star, brighter than the others, but not qualitatively different. Not warm, not large, not the organizing center of a visible sky. There is no sky. There is no up or down. There is no ground. There is no temperature that a human body could survive. There is no sense of distance from nearby objects, because there are no nearby objects. There is no sense of motion, because there is nothing relative to which the motion is apparent. If you could somehow exist at Voyager's location, what you would experience is not the dramatic emptiness of science fiction, where spaceships fly through visually interesting fields of gas and light. You would experience nothing. An absolute, featureless dark, punctuated only by the distant light of stars, none of them close enough to illuminate anything. None of them warm enough to feel. The nearest anything is trillions of kilometers away in every direction. The nearest light that would feel like light to a human body is the sun, which from there is simply a bright point in an otherwise unbroken dark. Voyager 1 has been in that place for over 12 years. The machine does not know it is there. The machine does not experience the isolation. But the isolation is real, and it is absolute, and it is permanent in any time frame that matters to the people who built the machine, and the people who manage it, and the people who will eventually turn off the last instrument and acknowledge that the conversation has ended. In 1977, the outer planets of our solar system arranged themselves in a configuration that occurs roughly once every 176 years. Jupiter, Saturn, Uranus and Neptune fell into a kind of arc across the outer solar system, a sequence of gravitational stepping stones positioned in a geometry that made it possible to visit all four of them in a single mission. Not by carrying enough fuel to travel directly from one to the next, which would have required an impossible amount of propellant, but by using the gravity of each planet to accelerate the spacecraft toward the next one. A chain of free speed, paid for by the momentum of the planets themselves. The next time this geometry will occur is sometime around the 2150s. No one alive today will see it. The scientists and engineers who designed the Voyager mission knew exactly what they were working with. They understood the alignment would not come again in their lifetimes, or in the lifetimes of their children. They understood that if the mission was not built and launched during this specific window, the opportunity would close for over a century, and the next generation of scientists who might attempt it would have to start over with different technology and different budgets, and no institutional memory from this one. So they designed two spacecraft in that knowledge. They built them to take advantage of this specific geometry, to fly this specific path, to use these specific planets in this specific order. The mission existed because the window existed. The legacy came later, unbidden. The technique the mission depended on is called a gravity assist, sometimes called a gravitational slingshot. When a spacecraft passes close to a massive planet, the planet's gravity pulls the spacecraft toward it, accelerating it as it approaches. If the trajectory is calculated correctly, the spacecraft swings around the planet in a curved arc and is flung outward in a new direction, carrying significantly more speed than it arrived with. The planet loses an almost unmeasurably tiny fraction of its own orbital energy. The spacecraft gains a boost that would otherwise have required an enormous quantity of fuel to achieve. Think of it this way. A ball rolling slowly across a floor gains nothing from a stationary wall. But if the wall is moving toward the ball in the right direction at the right angle, the collision transfers energy. The ball leaves faster than it arrived. The wall barely notices. Scale that principle up to a spacecraft on a planet the size of Jupiter, which has more than 1,300 times the volume of Earth and a gravitational field to match, and the energy transfer becomes enormous relative to the mass of the spacecraft. Jupiter barely notices. Voyager gained velocity it would otherwise have needed tons of fuel to achieve. Voyager 1 used Jupiter as its first slingshot. The spacecraft arrived at Jupiter in March of 1979, roughly 18 months after launch. Jupiter's gravity pulled it into a close approach, accelerated it significantly, and flung it outward in a new direction toward Saturn. Voyager 1 reached Saturn in November of 1980. Saturn's gravity added more speed and bent the trajectory upward, out of the plane in which most of the planets orbit, putting Voyager 1 on a path that would carry it away from the solar system entirely. Without the planetary alignment and the gravity assists it made possible, reaching the distances Voyager 1 has achieved in 49 years would have been practically impossible with any rocket available in the 1970s. The fuel required to achieve those speeds through direct propulsion would have far exceeded what any launch vehicle could lift. The 1977 window turned an impossible mission into a difficult one, and a difficult one into the most successful long-duration spacecraft mission in history. The computers on board Voyager 1 have roughly 3 million times less memory than a modern smartphone. The people who designed the trajectories worked with computing systems that took hours to verify calculations that a modern laptop could finish in seconds. They drew orbits on paper first. They checked their math by hand before feeding the numbers into a computer. The trajectory that has carried Voyager 1 to interstellar space was calculated by people using tools that most children today would consider antique. Those calculations have been correct for 49 years. The mission was not designed with legacy in mind. There were no speeches at the design meetings about humanity reaching beyond the solar system, about the philosophical weight of the undertaking, about what it would mean to send something that would outlast everything familiar. The mission was designed because the window existed, and the science was worth doing, and there was no reason to wait. The meaning that has accumulated around it since, the scientific discoveries, the cultural weight, the haunting questions it has raised about scale and permanence and silence, none of that was written into the design documents. It arrived on its own, slowly, as the decades passed and the machines kept going, and the distances grew so large that even the most experienced planetary scientists had to occasionally stop and simply be still with what had been made. There is something worth sitting with in the particular timing of the mission. The planetary alignment of 1977 was not discovered late. Astronomers had known for years that the window was coming, and they had been arguing for years about whether and how to use it. The design and construction of the Voyager spacecraft took place in an environment of uncertainty. Uncertain funding, uncertain scientific priorities, uncertain institutional support. The mission was nearly cancelled multiple times before it launched. The decision to go ahead with a mission capable of visiting all 4 outer planets was not obvious or inevitable. It was argued for and fought for and funded incrementally and built under pressure. The people who launched Voyager 1 into that window did not know what would come back from Jupiter, or Saturn, or the space beyond. They knew the science was worth attempting. They knew the window would close and not reopen. They knew that if they did not go now, no one would go for another century and a half. That knowledge was enough to carry the mission from drawing board to launch pad. The meaning that accumulated afterward was not theirs to plan for. It arrived on its own as the machines kept going and the data kept coming, and the decades kept passing and the distances kept growing until the original purpose of the mission, to photograph the outer planets up close, seemed almost like a footnote compared to what the spacecraft had become. Before Voyager, Jupiter was a coloured smear in a telescope, not a world, not a place. A disk in an eyepiece, banded with orange and yellow, beautiful in a distant way, but without texture, without detail, without any of the qualities that make a viewer feel they are looking at something real rather than an illustration. Astronomers had studied it for centuries. They knew its size, its mass, its approximate composition. They had tracked the Great Red Spot across its southern hemisphere for generations, noting that this persistent oval feature had been visible since at least the 17th century. They had catalogued its 4 large moons, first observed by Galileo in 1610 and studied with increasing precision in the centuries since. They knew a great deal about Jupiter, in the way you can know a great deal about a place from maps and second-hand descriptions without ever having been there, without ever seeing what the light actually looks like, without ever having data from the surface of that place, rather than filtered through 150 million kilometers of empty space. Voyager 1 arrived at Jupiter in March of 1979 and changed that permanently. Jupiter's atmosphere, seen at close range for the first time, was a churning, turbulent system of interlocking cloud bands and jet streams, moving in opposite directions at speeds that had no equivalent on Earth. Neighbouring bands of atmosphere could move in completely opposite directions simultaneously, separated by boundaries where the shear between them produced visible turbulence, visible from thousands of kilometres away. The cloud structures that looked smooth and orderly from Earth were revealed to be intricate, layered systems of rising and falling gas, of eddies and vortices and convective plumes extending deep into the atmosphere, where increasing pressure and temperature produced conditions unlike anything in our experience. The Great Red Spot, which from Earth had always appeared as a quiet and stable oval feature on Jupiter's southern hemisphere, was revealed to be an active, rotating storm system large enough to contain multiple copies of Earth inside it. Its winds extended hundreds of kilometers deep into the atmosphere. It had been turning continuously for at least 3 centuries by the time Voyager photographed it, possibly for much longer, and the mechanism that sustains it through all that time was still not fully understood then, and is still not fully understood now. But the most surprising discovery at Jupiter did not come from the planet itself. It came from a moon, and it arrived by accident 3 days before closest approach. A navigation engineer named Linda Morabito was examining a long exposure photograph of one of Jupiter's large moons, a body called Io. The photograph had been taken for navigation purposes only, to help the team calculate the spacecraft's precise position relative to the moon. She was looking at it for navigational data, not for science. But on the edge of Io's disk, arching above the limb of the moon in a graceful umbrella shape that extended well beyond the surface, was a feature that should not have been there. It was far too large to be a shadow effect. It was too bright to be a simple surface feature. It had a structure, a shape, that suggested something rising above the surface and dispersing into space. Within hours, the team concluded that what Morabito had seen was an active volcanic eruption in progress, captured in real time by a camera that had been pointed at the moon for entirely different reasons. Io was not a geologically quiet body. It was the most volcanically active world in the entire solar system, covered in hundreds of active volcanoes, lava lakes glowing orange and red across its surface, and sulfur dioxide plumes rising hundreds of kilometers above the ground and falling back as deposits in colors that ranged from white to yellow to orange to black. A theoretical paper predicting that Io would show evidence of tidal heating had been published just days before the flyby, almost simultaneously with the observational confirmation. The prediction and the discovery met each other at the moment of closest approach. As though the solar system had waited until someone was watching before revealing what it had been doing all along. Every image, every measurement at Jupiter was taken in a single pass. The spacecraft approached at tens of thousands of kilometers per hour. The window of closest approach lasted hours. There was no option to orbit, no option to slow down, no second chance to look at something that had turned out to be more interesting than expected. After the encounter, Jupiter fell behind, shrinking in the rear frame as the spacecraft accelerated outward, and it was gone. The planets were not the destination, they were the road. Each one was a farewell made at high speed, with no return scheduled. What Voyager revealed at Jupiter mattered not just as data, but as a correction to a particular kind of assumption. Before the flyby, it was possible to believe that the solar system was effectively understood in outline. The planets were known. Their sizes and masses were measured. Their moons were catalogued. The fundamental structure of what we lived in had been mapped well enough that the remaining work seemed like filling in details. Io changed that. The most geologically active body in the solar system had been right there, orbiting Jupiter, for as long as Jupiter had existed, erupting continuously for billions of years, and we had not known. Our best telescopes, our best scientists, our best models had looked at Io and seen a moon, not a furnace. The discovery did not come from a dedicated scientific observation or a new theory. It came from a navigation engineer looking at a photograph taken for entirely different purposes, noticing something that was not supposed to be there. The solar system is not understood in outline. It was not understood in outline in 1979, and it is not understood in outline now. Every close look at any object in it has produced surprises. Not minor deviations from expectation, but fundamental revelations about what the place actually is. Jupiter's moons were not simply smaller versions of the Moon. They were their own worlds, with their own geological histories, their own chemical complexity, their own evidence of processes that textbooks had not anticipated. Every flyby produced this same quality of correction. What we thought we knew, measured from a distance and projected forward through our models, was incomplete in ways we could not have identified without going there. After Jupiter, Voyager 1 aimed for Saturn and arrived in November of 1980. Saturn's rings, which from Earth appear as smooth and elegant bands surrounding the planet in a kind of architectural perfection, were revealed up close to be something entirely different. Not decoration, not a few smooth, flat bands of material. The Voyager images showed thousands of individual ringlets, each slightly different from the ones beside it, separated by gaps of varying widths and wave patterns that moved through the ring material like ripples crossing the surface of a shallow pond disturbed by a passing stone. The gaps themselves were not empty, they contained thinner concentrations of ring material, shaped and herded by gravitational resonances with Saturn's moons orbiting farther out. Particles ranged in size from fine dust to chunks of ice as large as houses, all orbiting at slightly different speeds, all confined by the same gravitational physics into bands so proportionally thin, relative to their width, that if you scaled the rings to the diameter of a sheet of paper, the paper would need to be thinner than a single molecule. The beauty was real, but it was a product of distance and angle. Saturn's rings seen from Earth are a beautiful thing because they are far enough away and oriented correctly to look like a single object with coherent structure. Up close, they were a collision field, active and dynamic. Particles jostling and crashing at orbital velocities, the accumulated debris of material that had never quite coalesced into a moon and never quite dispersed entirely. After Saturn, Voyager 1 was done with planets. Its trajectory carried it upward, out of the plane of the solar system, onto a path that would take it into the outer reaches and eventually beyond. But Voyager 2, following a different and slower trajectory, continued outward and became the only spacecraft in history to visit both Uranus and Neptune. At Uranus, it found a planet tilted so severely on its axis that it effectively rolls through its orbit on its side, with its poles pointing roughly in the direction of its orbital path rather than perpendicular to it. The magnetic field is not centered on the planet or aligned with its rotational axis. It is offset significantly, generating a wildly asymmetric magnetosphere that creates conditions unlike anything seen around the other planets. The magnetic pole wanders in a pattern that does not match the planet's rotation in any simple way. Decades later, the origin of this extreme axial tilt and the unusual magnetic configuration remains incompletely understood. One leading theory involves a massive collision early in the solar system's history. Others suggest a more complex internal structure than models have so far been able to account for. Uranus presented a world that did not behave the way a planet was supposed to behave, and it has been offering more questions than answers ever since. At Neptune, Voyager 2 found winds moving at roughly 2,000 km per hour, faster than the winds of Saturn, despite Neptune being much farther from the Sun and receiving far less solar energy. Where that internal energy comes from is still an open question. Neptune has a massive dark storm feature visible in Voyager's images, and its largest moon Triton orbits the planet in retrograde, in the opposite direction from Neptune's rotation, indicating it was captured from elsewhere rather than formed in place alongside the planet. Triton is also geologically active, with geysers of nitrogen gas venting from its surface into a thin atmosphere above a surface of frozen nitrogen and methane. We have not been back to either Uranus or Neptune since. The Voyager 2 flyby of Neptune in August of 1989 remains the only close look humanity has ever taken at the outermost planets of our solar system. Those images and measurements, taken at high speed from a single pass more than 35 years ago, are still the most detailed data we have. No replacement mission has gone there. No follow-up probe has made the trip. We visited those worlds once, from a machine moving too fast to stop, and everything we know from close range comes from that single encounter, completed in hours, never repeated. The significance of the Neptune flyby in 1989 is not only what it showed, but what it ended. After Neptune, there were no more outer planets to visit. The grand tour was complete. Both spacecraft were now heading into the outer reaches with no further planetary targets on their paths. The mission that had been defined by what it was flying toward became, after Neptune, defined by what it was leaving behind. No generation of scientists since 1989 has had access to new close-range observations of Uranus or Neptune. The questions raised by the Voyager flybys, the strange axial tilt of Uranus, the offset magnetic field, the unexpected winds at Neptune. The retrograde orbit of Triton have been studied from Earth-based telescopes and from the Hubble Space Telescope, but none of those observations can replicate what a spacecraft in close proximity can do. The data from 1986 and 1989 is still the foundation of what we know about those worlds. There have been proposals for new missions to Uranus and Neptune. Scientists have argued for decades that the ice giants, as Uranus and Neptune are classified, represent an important and understudied class of planet, and that new missions could answer questions that Voyager raised but could not stay long enough to resolve. As of now, no such mission has launched. The planning documents exist. The scientific rationale is strong. The Voyager flybys are cited in every proposal as the evidence of what close observation can reveal. But Voyager is still the only spacecraft that has been there. And the images it took at high speed, in single passes, more than 30 years ago, are still the only close-range views we have of two of the four largest planets in our solar system. In 1990, with Voyager 1 now roughly 6 billion kilometers from the Sun, a scientist named Carl Sagan made a request he had been making for years. He had argued, since the late 1970s, that before the spacecraft left the inner solar system far enough behind to make it impossible, NASA should turn the cameras back toward home. Not toward any particular scientific target. Toward home. Toward the solar system seen from the outside, from a point of view that no camera had ever occupied. a photograph taken not to advance planetary science, but to show something about where this machine had come from, and what that place looked like from far away. NASA had been resistant. The technical risks were real. Pointing the camera in the general direction of the sun carried a risk of damaging the light-sensitive systems, the same way looking directly at the sun damages human eyes, except with no ability to look away quickly enough if something went wrong. The scientific value of the images was debatable. Every member of the science team could point to other uses for the power and the data allocation. Every argument the engineers made against the photograph was reasonable. Sagan continued making the argument. He made it through the 1980s as the spacecraft continued outward and the cameras continued operating. He made it with enough persistence and with enough persuasiveness that eventually in 1990 permission was granted. The cameras were reactivated. A series of 60 images was taken, covering most of the planets visible from that distance and angle. And in the image of Earth, our planet appeared as a tiny point of pale blue light, barely distinguishable from the scattered rays of sunlight crossing the frame like searchlight beams through dust. Earth occupied roughly 1/12 of a single pixel. The entire Earth, with every mountain and ocean, every city that had ever been built, every war that had ever been fought, every person who had ever lived on it, was a fraction of a picture element so small it was nearly invisible in a frame dominated by darkness and scattered light. If you printed that image large enough to see Earth clearly as a recognizable disk with continents and oceans, the print would need to be roughly the size of a city block. Carl Sagan wrote about the photograph later. He described Earth as a mote of dust suspended in a sunbeam. He wrote about the rivers of blood spilled by conquerors so that in glory and triumph they could become momentary masters of a fraction of a dot. He described the pale blue dot as a very small stage in a vast cosmic arena, and the torrents of cruelty and misery inflicted by the inhabitants of one corner of that dot on the scarcely distinguishable inhabitants of some other corner as the complacency of nations, the vanity of religions. His words have been read many times in the decades since. They remain accurate. The image has not changed. The distances it reveals have not shrunk. But here is the other thing the photograph was, in purely practical terms. It was the last image of Earth that Voyager 1 ever took. After the family portrait session was complete, the cameras were shut down and never turned back on. There was no longer a scientific reason to run them. The spacecraft was heading into a region where there was nothing nearby to photograph. The cameras consumed power that was needed elsewhere for instruments that could still contribute data that no other source could provide. The shutdown was straightforward from an engineering perspective. It was also permanent. The camera that took humanity's most quietly devastating photograph of itself was switched off immediately after the photograph was complete. The machine that carried it kept going, accelerating away from everything familiar at 61,000 kilometers per hour, carrying no means to record the recession of the only home it had ever known. The pale blue dot grew smaller, then smaller still, then invisible, then unreachable even in theory from any instrument on board. From where Voyager 1 now travels 170 astronomical units from Earth, the Sun is simply a bright star. Earth is not visible at all from that distance. The last time any camera on Voyager 1 captured an image of the planet where it was assembled, it was 1990, from 6 billion kilometers. That was close, by the standards of where the spacecraft has gone since. That was the goodbye. Almost not taken at the last possible moment. And then the camera was switched off, and the machine kept going. The photograph came close to not being taken at all. The technical concerns were real, and the scientists who argued against it were not being obstructionist. Pointing Voyager 1's camera in the general direction of the Sun carried genuine risk of damaging the optical systems. Every instrument on the spacecraft was precious, because every instrument was irreplaceable. Damaging the camera for a photograph that had no direct scientific value was not a trivial risk. The engineers who worried about it were doing their jobs. But Sagan's argument was not about scientific value in the ordinary sense. It was about a different kind of value, harder to quantify, easier to dismiss, and ultimately impossible to obtain any other way. The argument was that a photograph of the solar system from the outside, from a point of view that no camera had ever occupied, and that no camera might occupy again for a very long time, had a kind of meaning that transcended its scientific utility. That's seeing our own solar system from outside it, seeing Earth as one small element in a larger structure, rather than as the centre around which everything else was organised, would do something to human understanding that no telescope pointed at other stars could do. Permission was eventually granted. The photographs were taken. The camera was turned off immediately after. The risk that had been weighed so carefully was not realised, and the images existed, and they have been looked at millions of times in the decades since by people who have felt in them exactly the thing Sagan had argued they would feel. The moment after the shutter closed for the last time on Voyager 1's camera was the moment the spacecraft stopped looking back. From that point there was only forward, into a darkness it had no eyes to see. For most of its time in flight, Voyager 1 was still inside something. Not a structure with walls, nothing visible, but a real, measurable physical region, a bubble of influence that our Sun generates around itself and extends outward in all directions through the solar system and beyond. This bubble is called the heliosphere, and it is shaped by the solar wind, a continuous outward flow of charged particles, mostly electrons and protons, that streams away from the Sun in every direction at speeds of several hundred kilometers per second. Think of the Sun as a boat moving through the galaxy. The boat pushes water aside and creates a wake. The Sun pushes through the interstellar medium, the thin gas and magnetic field that fills the space between stars, and creates an enormous cavity around itself. That cavity is the heliosphere. Inside it, the Sun's particles and magnetic influence dominate. Outside it, the galaxy does. The solar wind carries the Sun's magnetic field stretched outward like an inflated skin over the entire solar system. This extended magnetic field deflects a significant portion of the high-energy cosmic rays that move through interstellar space. Cosmic rays are energetic particles, mostly protons, accelerated to near light speed by violent events elsewhere in the galaxy, by supernovae, and the shockwaves of ancient stellar explosions and other processes that have been running since long before our solar system existed. Inside the heliosphere, the Sun's magnetic influence reduces the most dangerous of these. It is not perfect shielding, but it is real, and it has been operating silently around every planet in our solar system for billions of years. The heliosphere does not end abruptly. It tapers. Moving outward from the Sun, the solar wind eventually encounters increasing resistance from the interstellar medium, the pressure from outside growing as the Sun's particles spread thinner over an ever larger volume of space. At a boundary called the termination shock, the solar wind slows dramatically, transitioning from supersonic to subsonic speeds the way a sonic boom marks the transition through the sound barrier in reverse. Beyond the termination shock is a turbulent zone called the heliosheath, where the slowing solar wind piles up and compresses, heated by the collision. And then there is the heliopause, the final boundary, where the solar wind pressure and the interstellar medium pressure reach equilibrium, and the Sun's direct influence ends. beyond the heliopause is interstellar space, the actual space between stars, the environment that belongs to no particular sun, shaped by the collective influence of the entire galaxy, carrying particles from stellar explosions that happened millions of years ago, threaded by magnetic fields that extend across thousands of light years. Voyager 1 crossed the heliopause in August of 2012. The instruments registered the change precisely. The density of solar particles dropped sharply. The density of galactic cosmic ray particles increased. The magnetic field changed in character in ways consistent with crossing from one physical environment into another. The data arrived at JPL after a communication delay of over 17 hours. Scientists analysed it from multiple independent approaches. Every analysis reached the same conclusion. Voyager 1 was no longer inside the heliosphere. It was in interstellar space. No human-made object had ever been there before. For 4.5 billion years, the heliopause had existed with no instrument able to sample the environment on its outer side. Voyager 1 crossed it and became the first machine to report back from the other side of the boundary that separates our star from the rest of the galaxy. Voyager 2 made the same crossing in November of 2018, on a different trajectory through a different region of the heliopause. Its instruments registered the same basic transition, while also revealing differences that suggested the boundary is not uniform in structure. We now have direct measurements of interstellar space from two separate points, taken by instruments designed in the 1970s, operating decades beyond their original design specifications, at distances that the people who built them could calculate theoretically, but had never measured. Voyager 1 crossed the heliopause 35 years after it launched. 35 years. An entire human generation spent travelling, just to reach the edge of our own star's local territory. Some of the scientists who designed the instruments that made the measurements in 2012 had already retired. Some were no longer alive. The machines they had built completed the measurement and kept going, carrying instruments that were still working, still measuring, in a place where no measurement had ever been made before. Outside the heliopause, the universe is harder. The cosmic ray environment is more intense. The particles around Voyager are now shaped by other stars, by the ancient history of the galaxy, by events that happened before our solar system formed. The sun cannot reach there. The magnetic influence that has defined the physical environment of every planet and moon in our solar system for billions of years stops at the heliopause. And beyond it, our star is just one among hundreds of billions, its local territory bounded and finite, its influence confined to the bubble it maintains around itself. Voyager 1 is outside that bubble. It has been for over 12 years. The measurement of Voyager 1's crossing was not simple or immediate. The data arrived over months and was analysed by multiple independent teams using different methods before a consensus emerged. Scientists had been predicting the location of the heliopause for decades, and their predictions had varied considerably, ranging from perhaps 80 astronomical units to perhaps 150 or more. The heliosphere is not symmetric. Its shape is affected by the direction of the interstellar medium flowing past it, and by variations in solar activity over the decades. Voyager 1 crossed in one specific direction at one specific location, and that data tells us about one point on a surface that extends in all directions around the Sun. Voyager 2's crossing in 2018, on a different trajectory and through a different region of the heliopause, provided a second independent measurement. The two crossings were different in detail, in ways that revealed something about the structure of the boundary. The region where Voyager 2 crossed showed different characteristics from where Voyager 1 crossed, suggesting that the heliopause varies across its surface in ways that single-point measurements cannot fully characterize. To map the full structure of the heliosphere's outer boundary would require many more crossings, from many different directions. We have two data points on the boundary that separates our star's local environment from the rest of the galaxy. Two measurements made by instruments designed in the 1970s, operating on power that has been declining since the day they launched. Two confirmations that the heliosphere is real and measurable and bounded, and that the universe beyond it is a different physical environment from the universe within it. For 4.5 billion years, no instrument had measured this. For the last 14 years, two have. There are no solar panels on Voyager 1. At the distances it travels, sunlight arrives with roughly 23,000 times less intensity than it reaches Earth. Solar panels capable of generating useful electricity at those distances would have needed to be impossibly large, far beyond what any rocket could have lifted. The design required a different solution, one that did not depend on the sun at all. Voyager 1 runs on 3 devices called radioisotope thermoelectric generators. Each one contains a core of plutonium-238, a radioactive element that releases heat as its atoms undergo natural decay. That heat is converted into electricity by thermocouples, devices that generate a small voltage when one end is hot and the other is cold. The hot end sits against the plutonium core. The cold end faces the vacuum of space. The temperature difference between them drives the current. Think of it as a campfire that has been burning since 1977. Not with flames, not with combustion, but with the deep, slow heat of atomic decay, releasing energy at a rate determined by physics rather than by anything we can control. The fire does not burn brighter or dimmer because of anything we do. It follows its own schedule. There are no moving parts in this system, no combustion, no fuel being burned. The plutonium decays at the rate physics dictates. Releasing heat, the heat becomes electricity, and the electricity keeps the spacecraft alive. The system has been operating continuously for nearly 50 years, through close planetary flybys and the extreme cold of the outer solar system and the even more extreme emptiness of interstellar space, without a moving component to wear out. But plutonium-238 has a half-life of approximately 87.7 years. Every 87 years, roughly half of the remaining plutonium atoms will have completed their decay and will no longer contribute to the heat output. The decline is not sudden, it is gradual, continuous, and mathematically predictable. Every year, a measurable fraction of the remaining atoms transform. The heat output decreases by a small corresponding amount. The electricity available to the spacecraft decreases accordingly. The combined RTGs on Voyager 1 launched with a total output of roughly 470 watts. That is modest by any modern standard, but it was enough in 1977 to power all 10 science instruments, the computers, the transmitter, the attitude control systems, and the heaters that prevent the spacecraft's fuel lines from freezing in deep space. 49 years later, the RTGs are producing less than half of that original output. The decline has been approximately 4 watts per year on average. The math is not complicated. 4 watts per year for 49 years is close to 200 watts of lost output. The power budget is now thin enough that every system on the spacecraft requires careful management. 4 watts per year sounds small. Consider what it means in practice. Every year the spacecraft has 4 fewer watts to work with than it had the year before. 4 watts is not enough to notice in a house. In a spacecraft with no way to recharge, no way to refuel, no way to add any power at all, 4 watts is a decision. It is a heater turned off. It is an instrument shut down. It is the slow closing of options, one at a time over decades, with no reversals possible. Voyager 1 is not running low on power because something went wrong. It is running low on power because something went exactly right for so long that physics has finally begun to close in on the margins. The mission is not failing, it is fading. There is a difference between those two things, and it is important. The machine that first measured the interstellar medium, that confirmed for the first time what lies on the other side of the heliosphere, that has been returning data for longer than most of the people managing it have been alive, is fading. 4 watts at a time, year by year. Quietly and irreversibly. The experience of managing a mission under this kind of power constraint is one that has no real parallel in other engineering contexts. On Earth, when a system runs low on power, you can add power. You can replace a battery, plug in a cable, start a generator, connect to the grid. The solution to insufficient power, in nearly every context humans have ever worked in, is to obtain more power from somewhere. There is no somewhere for Voyager 1. The power available to the spacecraft is exactly what the decaying plutonium provides, no more. Every year there is less of it. Every year the team makes decisions about what to keep running with less margin than they had the year before. Every decision to shut something off to save power is a decision that cannot be reversed. The instrument that is turned off to conserve the power budget will not be turned back on, because the power that was being consumed by that instrument is needed by something else, and the next year there will be even less. The engineers managing this situation have developed a particular kind of relationship with the power budget. They track it precisely. They model future scenarios. They estimate how long each remaining system can be sustained. They make decisions years in advance about the sequence in which systems will be shut down, trying to optimize the scientific return from the time remaining while keeping the essential operational systems functional as long as possible. Essential operational systems means the transmitter and the attitude control that keeps the antenna pointed toward Earth. Everything else is optional in the sense that the mission can continue without it. The instruments are the reason to continue, but the transmitter and the attitude control are what makes continuation possible. When the power can no longer sustain both, the instruments will go and the transmitter will stay, for as long as the transmitter itself can be maintained. After the transmitter, there is nothing. The cameras went off in 1990. That was the first major instrument shutdown, timed deliberately to coincide with the pale blue dot photographs, which provided a final scientific purpose for the imaging systems before they were switched off to conserve power. The cameras had done their work at Jupiter and Saturn and in the family portrait of the solar system. There was nothing left nearby to photograph. The power they consumed was needed elsewhere. The shutdown was permanent. After the cameras came the ultraviolet spectrometer, which had been studying the ultraviolet emissions of the interstellar medium. Then the plasma science instrument, which had measured the properties of the solar wind during the long transit outward. Then others, in sequence, each one evaluated the same way. What does this instrument still need to tell us, compared to what it costs to keep running? Each calculation resulted in the same kind of answer. The instrument had completed its primary work. The power was needed elsewhere. Turn it off. In February of 2025, engineers turned off the cosmic ray subsystem on Voyager 1. That instrument had been measuring the flux and energy distribution of cosmic rays since the spacecraft launched in 1977. It had been one of the key instruments in the analysis that confirmed the heliosphere crossing in 2012. It had operated for 47 years. the shutdown freed a small amount of power, enough to keep other things running a little longer. On April 17th of 2026, the low-energy charged particle instrument was shut down. The command was sent from JPL that morning. It travelled at the speed of light for 23 hours and 32 minutes before it arrived at the spacecraft. The instrument powered down. A small motor inside the LEPI was left running, a quiet acknowledgement that these engineers have learned not to close doors entirely until they absolutely must. They have been surprised before by this machine, but the instrument is off, and the expectation is that it will stay off. Karim Badruddin, the Voyager mission manager, said after the shutdown, while shutting down a science instrument is not anybody's preference, it is the best option available. Those words describe something real. The mission team did not want to shut it down. They made the decision because the alternative was worse. Voyager 1 now carries 2 active science instruments. The plasma wave subsystem detects waves and oscillations in the plasma of the interstellar medium. In 2023, it picked up a faint, persistent oscillation that allowed scientists to measure the density of interstellar plasma with a precision that had not previously been achieved. That measurement was made by a 46-year-old instrument running on power that has been declining for nearly 5 decades. From a distance so great that the data takes nearly a full day to arrive. The measurement was published in scientific journals. Other scientists studied it. It contributed to the understanding of interstellar space in ways that nothing else could have. The magnetometer measures the direction and strength of the magnetic field in interstellar space. The interstellar magnetic field carries information about the history of the galaxy, about the remnants of stellar explosions that happened long before our solar system formed, about processes that have been shaping the space between stars for billions of years. No other instrument has ever measured this field from this location. These 2 instruments are what remains. Both are working. Both are returning data that cannot be obtained any other way. And both are running on a power supply that will continue to decline at roughly 4 watts per year until there is no longer enough to run them. The instruments that measured the historic crossing of the heliopause in 2012 are mostly gone. The machine that first told us what interstellar space feels like is slowly losing the ability to feel anything at all. Not because it failed, because it has been succeeding for so long that physics has finally caught up with what we asked of it. Each instrument shutdown has its own history, its own arguments, its own moment of decision. The teams who designed those instruments, who calibrated them, who built the software to process their data, who spent careers analysing what they returned, have had to participate in decisions to turn them off. In some cases, the scientists who built an instrument were still active in the field when it was shut down. They received the data it had returned for decades, published papers based on it, built careers around understanding what it measured, and then had to agree that it was time to turn it off. The cosmic ray subsystem, shut down in February of 2025, had been one of the instruments that contributed most directly to confirming the heliosphere crossing in 2012. It measured the flux of cosmic rays entering the solar system from interstellar space, and its data showed the sharp transition from solar-dominated to galactic-dominated particle populations that marked the boundary. After the crossing was confirmed, and the instrument had returned years of measurements from interstellar space, the power budget calculation eventually reached a point where running it was no longer the highest priority use of the available watts. The LEP, shut down in April of 2026, had provided a complementary view of the particle environment throughout the mission. It measured lower energy charged particles, filling in the energy spectrum that other instruments could not cover. Its measurements contributed to the picture of what interstellar space actually contains, the composition and energy distribution of the particles that fill the space between stars. And then the power calculation caught up with it too. What remains is the magnetometer and the plasma wave subsystem. The magnetometer provides what may be the most fundamental measurement of interstellar space that Voyager can make: the direction and strength of the magnetic field threading the medium between stars. The plasma wave subsystem listens for wave patterns that reveal the density and turbulence of the surrounding plasma. Together they are measuring the basic electromagnetic structure of interstellar space from a single, slowly moving point within it. When they go dark, that point of measurement will go dark with them. There is no replacement coming. Voyager 1 is not carrying only instruments. Attached to its body, as it has been since the day it launched, is a 12-inch disc made of copper and plated with gold. A phonograph record, analog format, encoding information in physical grooves cut into the surface. Analog was chosen deliberately because it can be decoded from first principles. Anyone who understands that a groove can cause vibration, and that vibration encodes sound, can work out the playback method without needing to know any specific digital standard. The instructions are engraved on the disk's surface itself, using the physics of the hydrogen atom as a universal clock, on the assumption that any civilization capable of retrieving an object from interstellar space would understand atomic physics well enough to follow the diagram. The disk contains 115 images, scientific diagrams showing human anatomy, the structure of Dinar, the solar system, and basic mathematical principles. Photographs of landscapes and oceans and forests and cities, images of human beings from different parts of the world doing different things, images of food, images of animals, images of the Earth from space. The disk contains greetings in 55 languages. The greeting in ancient Sumerian was recorded by a scholar, because there is no longer anyone alive who grew up speaking Sumerian as their first language. It is a dead language. No child has learnt it at a mother's knee for thousands of years. Voyager 1 is carrying words from a dead civilization into the universe, preserved in gold, moving at 61,000 kilometers per hour through a darkness that has no obligation to receive them. The disc contains 90 minutes of music. Bach's Brandenburg Concerto, Mozart's Magic Flute, Beethoven's Fifth Symphony, a Senegalese percussion piece, a Peruvian wedding song, a Georgian choral composition, an Australian Aboriginal song, Chuck Berry's Johnny B. Good, a Japanese koto piece. Music from traditions that share almost nothing with each other, except the fact that they were made by the same species on the same planet, selected over 6 weeks by a committee working under deadline, trying to say something true about a civilization in the time available. The disc contains sounds: rainfall, ocean waves, wind in trees, thunder, the calls of birds and whales and frogs, the sound of a human heartbeat. The first words a mother speaks to a newborn child, the sound of fire, the sound of... Carl Sagan, who chaired the committee that selected the contents, understood exactly what the odds were. He was not optimistic about encounter probability in any naive sense. He understood the size of the galaxy, the speed of the spacecraft, the mathematics of finding one small metal object among billions of cubic light-years of effectively empty space. He proceeded anyway. The nearest star in Voyager 1's general direction is thousands of light-years from making any meaningful close approach on any timescale less than geological. At the spacecraft's current speed, 1 light-year takes roughly 75,000 years to cover. For the record to be found, a civilization would need to be in the right part of the galaxy, have technology capable of detecting a metal object moving through interstellar space, choose to retrieve it rather than ignore it, and have sensory biology compatible with the frequencies in which the sounds and images are encoded. None of this is impossible. It is simply very unlikely in any time frame a human mind is built to contemplate. What the golden record actually is, then, is not a message sent with expectation of reply. It is a statement made without expectation of audience. It is the act of describing yourself to a universe that may never know you existed. A decision made in 1977 under a 6-week deadline that a civilization capable of launching something into interstellar space was a civilization worth introducing. The sounds are out there. The heartbeat is out there. The Sumerian greeting is out there. Moving through interstellar space in the cold and dark, encoded in gold, in a format that will remain physically intact for billions of years, in a universe that has not yet and may never acknowledge receiving them. We did not send the record because we thought it would arrive. We sent it because sending it said something about us that we wanted to be true. The 6 weeks spent assembling the golden record were not calm. The team worked under time pressure, without comprehensive access to recordings from all regions of the world, making choices that felt arbitrary even as they were being made, because any choice in 6 weeks necessarily felt arbitrary. Why this piece of music and not that one? Why this language and not another? Why this photograph and not a different one? The committee did not have good answers to these questions because there were no good answers. They had 6 weeks and the resources they could reach, and they made the best decisions they could under those conditions. Carl Sagan later described the experience as one of the most challenging and humbling of his life, not because of the physics or the engineering, but because of the question it forced on the committee. What do you say when you are speaking for the first time to something that has never heard of you? What do you include in the introduction of an entire species to the universe? The question has no correct answer. It has only the answer you give in the time available. The committee gave the answer it could. Rain falling, ocean waves, a heartbeat. Music from Back to Chuck Berry, greetings in 55 languages, including one from a civilization that no longer exists. 115 images of a planet and the creatures that lived on it, all of it encoded in analog format in the physical structure of a disk that would outlast everything it described. The record has been moving through interstellar space for nearly half a century. The people who assembled it are old now or gone. The studio where the recordings were made still exists in a different form. The world it described has changed in countless ways since 1977. The languages it contains have evolved. The music it includes has been succeeded by decades more of human music that is not on the record. The photographs it shows are now historical documents. The record does not know any of this. It carries what it was given and moves where the physics takes it, and will continue doing so long after every version of this sentence has been forgotten. Before the last signal fades, there is still data arriving. Right now, as you listen to this, 2 instruments on Voyager 1 are measuring the interstellar medium and sending their measurements back toward Earth. The data travels at the speed of light for nearly 24 hours before it arrives. The signal, when it reaches the receiving antennas, carries a power of roughly 20 billion times less than what it takes to run a digital wristwatch. 20 billion times less than a wristwatch. And yet it arrives. And yet it is detectable. And yet useful science is extracted from it and published and read and built upon. The Deep Space Network makes this possible. 3 antenna stations positioned around the globe take turns pointing their enormous dish antennas at the patch of sky where Voyager 1 currently sits. The largest of these antennas are 70 meters across, roughly the width of a professional football field. They are among the most sensitive radio receiving systems ever built, designed specifically for the task of extracting useful information from sources so faint that no ordinary receiver would register anything but static. The data arrives at 160 bits per second. To give that number a reference point, a single second of audio on a modern smartphone is encoded at rates typically thousands of times higher than that. A single photograph taken on a modern phone contains more data than Voyager 1 can transmit in several hours. The data rate is roughly comparable to the dial-up internet connections that were considered slow even in the early 1990s, except that those connections were transmitting data across telephone lines spanning a few hundred meters. And Voyager 1 is transmitting across 15.5 billion miles of interstellar space using a transmitter running on less than 20 watts of power. The data still arrives. Scientists still read it. The magnetometer is returning measurements of the interstellar magnetic field that exist nowhere else in the scientific record. The plasma wave subsystem is detecting oscillations in the surrounding plasma that tell scientists things about the structure and density of interstellar space that no model or telescope observation can provide. In 2023, the plasma wave subsystem detected a faint, persistent low-frequency oscillation that allowed scientists to measure the electron density of the interstellar medium with a precision that had not previously been achieved. That measurement was made by a 46-year-old instrument operating on power that has been declining for nearly 5 decades. From a location so remote that the data it recorded took nearly a full day to cross the distance between the instrument and the people who would analyze it. The mission team is doing something that has no real precedent in human experience. They are maintaining a functional relationship with an object so far away that the relationship itself is conducted in days rather than moments. Commands are sent that arrive tomorrow. Data arrives that was measured yesterday. Every decision is made based on information that is always at least a day old, about a machine that exists in conditions no human has ever experienced, in a place no human will ever go, that cannot be visited or inspected or repaired in any way. Some of the people on the Voyager mission team have been working on it for decades. Some were young engineers when the spacecraft launched, and are now in the final years of their professional lives. The spacecraft they built when they were young is still returning data. It has not stopped. It has continued operating for longer than any human mission in history, in a location no mission has ever reached, returning information that no other source can provide. They cannot visit the spacecraft. They cannot replace any component on it. They can send instructions that arrive tomorrow. They can receive data that was measured yesterday. That is the full extent of what the relationship allows, and it is enough. Because the data that arrives is irreplaceable, and the science that can be done with it is worth the effort of maintaining the connection. The connection will not last forever. The power is still declining, 4 watts at a time, year after year. The instruments that remain will eventually have to be shut down as the instruments before them were. And at some point, the transmitter itself will no longer generate a signal strong enough to be detected across the distance that separates Voyager 1 from Earth. The antennas will listen and find nothing there, and the machine will keep going anyway. The patience required to maintain this connection across this distance and this communication lag is a specific kind of patience that is hard to develop and harder to sustain. Most engineering problems have feedback loops measured in seconds or minutes. A test is run. A result comes back. An adjustment is made. The adjustment is tested. The loop is tight enough to be responsive, to feel like a conversation between the engineer and the system. The Voyager mission's feedback loop is measured in days. Every test takes 2 days to complete. Every adjustment requires 2 days to validate. Every anomaly takes 2 days to investigate after it appears in the data. 2 more days to address once a response has been formulated. In an emergency, there is no real-time intervention. There is only the best decision that can be made with incomplete information transmitted to a machine that will act on it 2 days later. The team has learned to work within this constraint, not by eliminating it, but by anticipating everything they can. Before sending a command that could have irreversible consequences, they model the scenario extensively. They consider failure modes. They prepare contingency commands that can be sent quickly if the primary command produces unexpected results. They have developed a discipline of caution that comes from knowing that a mistake cannot be corrected quickly, that the 2-day lag between action and consequence means that any error has time to compound before it can be addressed. This discipline has worked. The mission has operated successfully for nearly 50 years under these constraints. The distance that makes the communication lag unavoidable is the same distance that makes the mission's location unique and its data irreplaceable. The last signal will not come with a warning. There will be no designed farewell, no planned final transmission, no countdown that the team can watch approach zero. The engineers will not know in advance exactly when the last usable signal will arrive, because the power decline is gradual and the threshold of detectability is not a sharp line drawn in physics, but a fading, a slow transition from clearly detectable to barely detectable to not detectable in the noise. One day the signal will arrive faint but clearly readable. Another day it will arrive at the very edge of what the antennas can extract from the background. And then, eventually, there will be a day when the antennas listen at the calculated position of Voyager 1, and there is nothing there that can be distinguished from the natural noise of the universe. The mission team will listen for a while longer, to be certain. These are careful and methodical people who have been working with this machine for decades and who have learned to be skeptical of absence before concluding it is permanent. They will point the antennas at the right patch of sky and wait and listen and wait again on different days and in different conditions and with different instruments if possible. And eventually, after enough time has passed with the same result, they will reach a conclusion that the signal is gone and that it is not coming back and that the mission has ended. The machine will still be moving when that conclusion is reached. It will be moving at 61,000 kilometers per hour in the same direction it has been moving since 1977, following the path that physics drew for it when Jupiter and Saturn flung it outward nearly half a century ago. There is nothing in interstellar space to slow it. No atmosphere, no friction, no magnetic field strong enough to significantly alter its trajectory. No gravitational body nearby enough to exert meaningful force on any timescale shorter than thousands of years. The laws of inertia, in the absence of forces to counteract them, are absolute. The object continues. It will continue until something acts on it, and in the emptiness of interstellar space, nothing will. The mission will end. The object will not. Those are two completely different events, and they will happen to the same machine at different moments that are separated by nothing more than the recognition on one side of a communications link that the other side has gone quiet. The moment the last signal fades will be the moment the mission ceases to be an active program, the moment the daily routines at JPL oriented around Voyager change from listening and responding to archiving and remembering. The spacecraft will not pause. It will not register the change. It will not know that the conversation ended. It will continue doing what it has been doing, moving outward and away, carrying its silent instruments and its golden record into a darkness that will not acknowledge the transition. There will come a day when JPL's tracking systems continue to calculate Voyager 1's position. updating the trajectory model based on the known physics of its path and the last confirmed measurements of its velocity and direction, even though the spacecraft itself can no longer confirm its own location by responding to commands. A trajectory known. A position calculated. A machine unreachable. The spacecraft will exist as a mathematical certainty in rooms where no one can hear from it. The silence when it comes will be final on our side. But Voyager 1 will not experience silence. It will experience the same thing it has always experienced, which is nothing at all, because it is a machine, and machines do not experience. It will move and it will carry and it will pass through the interstellar medium at 61,000 kilometers per hour, and the universe will not mark the occasion of the last signal any more than it marked the occasion of the first. After the mission ends, there will be a period during which Voyager 1's position is still being calculated, still being updated, still being tracked by the systems that have tracked it for decades. The trajectory is known with high precision. The physics governing it in the absence of significant gravitational perturbations are well understood. The position calculation can continue updating in real time for as long as anyone maintains the software that does it. But there is a difference between knowing where something is and being in contact with it. For nearly 50 years, knowing where Voyager 1 was and being in contact with it were the same thing. The position was confirmed by the signal. The signal confirmed the position. The two were coupled, and the coupling was what made the mission active rather than merely theoretical. After the signal ends, the position calculation will continue, but the confirmation will stop. We will know with high confidence derived from physics where Voyager 1 is at any given moment. We will not hear from it. We will not be able to send it instructions. We will not receive data from whatever it is moving through. It will exist as a calculated point in space, tracked by the same kind of analysis that tracks any object moving through the solar system, except that it will be in interstellar space, where the gravitational influences that shape trajectories are fewer and weaker, and the calculation is both more uncertain over long timescales and more stable over short ones. The last signal will not be dramatic. It will simply be the last in a long series of signals that have been arriving for nearly 50 years. The mission team will recognize it as the last only in retrospect, after enough time has passed without another signal to confirm that the silence is not a temporary anomaly but a permanent condition, and the machine will keep going regardless of when that recognition comes. In roughly 40,000 years, Voyager 1 will make its closest approach to another star. The star is called AC+ 793888, and it sits in the direction of the constellation Camelopardalis. The closest approach will bring Voyager within approximately 1.5 light-years of that star. 1.5 light-years is not close in any ordinary sense of the word. It is not a visit. It is not a flyby in any meaningful comparison to the Jupiter and Saturn flybys of the early mission. It is the cosmic equivalent of passing through the same general ocean as a lighthouse, with the lighthouse so far away that you cannot see its beam, and the lighthouse so far away that it cannot see you, and the only connection being that your respective trajectories bring you closer to each other than to most other things in that region of space. The star will not notice. The spacecraft will not slow down. They will share a general neighborhood for a period measured in thousands of years, and then their relative motions will carry them apart. And the encounter will leave no record except in the trajectory calculations of any entity patient enough to track it. After that encounter, Voyager 1 will drift through the changing stellar neighborhood of the Milky Way over millions of years. Stars move relative to one another on these timescales, slowly by any ordinary measure but measurably when enough time passes. The Sun moves through the galaxy. the stars near the Sun move through the galaxy. The region of space that Voyager 1 currently occupies will look different in 10 million years, and different again in 100 million, and different beyond any resemblance to today in 1 billion. New stars will be nearby. Old stars that are currently nearby will be distant. The spacecraft will drift through stellar neighborhoods that no human civilization has named, and that no human mission will reach on any timescale that currently exists in planning documents. In the vacuum of interstellar space, there is no corrosion. Metal does not rust without oxygen, without liquid water, without significant ultraviolet radiation at close range, without the temperature cycling that expands and contracts materials and slowly works them apart, without the biological processes that break down complex chemical structures on planetary surfaces. The spacecraft structure will remain largely intact for a time period that dwarfs any human historical timescale. The gold-plated record is particularly suited to survive. Gold does not corrode. The copper beneath the gold plating, protected by it, does not corrode without oxygen. The physical structure of the grooves cut into the disk's surface will remain present indefinitely, as long as no physical force acts to damage them, and in the emptiness between stars, no such force is expected. In roughly 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin the process of expanding into a red giant. It will grow large enough to engulf Mercury, then Venus, then possibly Earth. The inner solar system, which has orbited this star for 4.5 billion years, will be consumed by the star that created it. When that happens, Voyager 1 will be approximately 85 light-years from its current position. The golden record it carries will still be intact. The grooves that carry the encoded sounds of rain falling on Earth, of a human heartbeat, of music from traditions that will by then have been gone for billions of years, will still be physically present in the surface of the disk. In roughly 4 billion years, the Milky Way galaxy and the Andromeda galaxy will begin a slow gravitational merger. Two galaxies colliding is not a collision in the ordinary sense. The distances between stars are so vast that individual stars almost never make physical contact during such a merger. But the gravitational dynamics reshape both structures over hundreds of millions of years, drawing them together, disrupting the orbital patterns of billions of stars, eventually producing a new merged galaxy. Voyager 1 will be somewhere inside that merged structure, one small metal object among hundreds of billions of stars, on a trajectory that was set by the alignment of 4 planets in 1977, on a planet that will by then have been gone for approximately 1 billion years. There is no natural process currently known that will destroy Voyager 1 on any timescale less than astronomical. The spacecraft will outlast the civilization that built it, the planet it was built on, and the star that warmed that planet. What comes after that, no current physics can reliably address. There is a question that the long-term trajectory raises without providing an answer, and it is worth sitting with rather than dismissing. In tens of thousands of years, in hundreds of thousands of years, in millions of years, as Voyager 1 drifts through the changing stellar neighborhoods of the Milky Way, what are the odds that any intelligence will ever encounter it? The answer depends on assumptions that cannot be made confidently. It depends on whether technological civilizations exist in the Milky Way beyond our own. It depends on whether any such civilization would have the means and the motivation to detect and retrieve a small metal object moving through interstellar space. It depends on whether the civilization's sensory biology and technological capabilities would allow it to recognize the record and decode it. Scientists who have thought carefully about this have generally concluded that the probability is very small on any timescale less than millions or billions of years. The galaxy is large. Voyager is small. The fraction of the galaxy's volume that Voyager will traverse on any reasonable timescale is a tiny fraction of the whole. Even assuming that technological civilizations exist throughout the galaxy, the probability that any one of them will happen to be in the right place at the right time to intercept an object as small as Voyager is extremely low. Carl Sagan understood this when he argued for including the record. The argument was not that the record would be found, it was that including it said something true about the civilization that launched the spacecraft, regardless of whether it was ever received. A species that decides it is worth describing, in the absence of any expectation of audience, has made a statement about its own self-understanding that stands independently of the outcome. The pyramids at Giza have stood for roughly 4,500 years. They are still standing. They are still recognizable as structures built by people with purpose and engineering skill. They have survived invasions and earthquakes and millennia of wind and weather. They are, by any reasonable human standard, extraordinarily durable. Tourists photograph them today as evidence of human capability to create things that last. But they are eroding. The limestone faces weather. Wind carries particles from the surface year by year. Rain works at the joints between stones over centuries. The original smooth white limestone casing that once covered the exterior is largely gone, worn away or removed over thousands of years. The capstones that once completed the geometry at the peak are missing. Given enough time, not millions of years but geological time, the pyramids will be reduced first to rubble and then to nothing distinguishable from the landscape around them. The material will remain, the structure will not. This is true of every monument humanity has built. Every building, every road, every library, every archive, every inscription carved into stone, every painting applied to a wall, every recording made on any medium. All of these things exist on Earth, in an atmosphere, in the presence of liquid water and oxygen and temperature cycling, and the countless chemical and biological processes that break down complex structures over time. Given enough time, nothing survives on a planetary surface. Nothing built by human hands, nothing natural, nothing at all except the planet itself, which will also eventually be consumed. Voyager 1 is not on a planetary surface. In interstellar space, in the complete absence of an atmosphere, without liquid water, without significant ultraviolet radiation at close range, without the temperature cycling that expands and contracts materials and works apart their joints, without the biological processes that eat through organic materials and chemical processes that corrode metals, the spacecraft structure decays at a rate so slow as to be irrelevant in practice on any timescale less than billions of years. The structure is aluminum and titanium and gold. In the conditions of interstellar space, these materials are extraordinarily stable. Aluminum does not corrode without oxygen. Titanium does not corrode without oxygen. Gold does not corrode under effectively any conditions that exist between the stars. The rate of decay for these materials in vacuum is not zero, but it is slow enough that billions of years need to pass before the degradation becomes meaningful. The golden record is particularly well suited to survive. The copper of the disk itself is protected by the gold plating. The gold does not corrode. The grooves cut into the copper surface, carrying the encoded sounds and images, will remain physically present in the disk indefinitely, readable in principle by anything that can make mechanical contact with the surface and detect the variations that the stylus would trace. The sounds of rain falling on Earth are encoded in those grooves. The sound of a human heartbeat is encoded in those grooves. The first words a mother speaks to a newborn child, music from traditions that have been practiced by human beings for thousands of years, all of it physically present in the surface of a disk that will still exist when the Earth it was made on is gone. When the civilization that made it has changed beyond any recognition or disappeared entirely. When the star it was launched toward has expanded and consumed what was once its planetary system. We build cities, and they fall. We write books, and they decay. We carve stone, and the stone weathers. We make recordings, and the recordings degrade, and the technologies that play them become obsolete, and the knowledge of how to use those technologies disappears. Everything we have made exists in the presence of entropy, and in an atmosphere, and in a world that is constantly working to undo the order we create. But we also launched 2 machines into interstellar space, and those machines will be intact and moving long after the last human city has crumbled, long after the last human book has turned to dust, long after the last carved stone has been worn smooth by time beyond counting. The most permanent physical record that human civilization has ever created is not in any museum. It is not in any archive. It is attached to a spacecraft moving through interstellar space at 61,000 kilometers per hour, and no one is taking care of it, and no one needs to. Because the universe itself, in the cold vacuum between the stars, is the most perfect preservative that the laws of physics allow. The contrast between what Voyager is and what surrounds it is worth sitting with in a specific way. The spacecraft was assembled by human beings in a building in California. It was tested in facilities designed and built by people whose names are in engineering records somewhere. It was launched on a rocket built by other people in another facility, using technologies developed over decades by still other people. Every component on it was touched by human hands, inspected by human eyes, decided on by human minds. And now it is in interstellar space, in a region that has never been touched by human hands, or inspected by human eyes, or decided on by any mind at all. The process that sent it there was entirely human. The place it has arrived in is entirely not. The spacecraft crossed a threshold, the heliopause, beyond which human presence in any physical sense ends, and has always ended and may always end, and it took everything we had put into it across that threshold and kept going. The most human-made thing in the universe is currently in the most inhuman place the universe has to offer in our immediate vicinity. It is surrounded by conditions that no human body could survive, at distances that no human vehicle could reach, in an environment that has been operating on timescales and scales that human civilization cannot comprehend except abstractly. And it is still transmitting, still returning data, still maintaining, however faintly and with however much delay, a thread of connection between that inhuman place and the very human room at JPL where people are sitting and listening. Voyager 1 has travelled, in 49 years of continuous motion, approximately 1.2% of the distance to the nearest star. 1.2%. The nearest star system is Alpha Centauri, at roughly 4.25 light-years from Earth. Voyager 1 is at roughly 0.0025 light-years. After nearly 50 years of travel, after becoming the farthest human-made object in history, after crossing the heliopause and entering interstellar space and providing measurements from a place no other instrument has ever reached, the spacecraft has covered 1.2% of the distance to the most accessible stellar neighbour in our galactic neighbourhood. The observable universe is roughly 93 billion light-years across. The Milky Way galaxy is roughly 100,000 light-years across. The distance to the nearest star is 4.25 light-years. The distance Voyager 1 has travelled from Earth is roughly 0.0025 light-years. If the Milky Way were scaled to the size of the continental United States, Voyager 1 would have moved approximately the width of a single human hair from its starting point. The comparison may actually be too generous. The width of a human hair is roughly 70 micrometers. The ratio of Voyager's distance to the diameter of the Milky Way is somewhat smaller than that. This is not offered as a criticism of the mission. The mission is a genuine achievement, one of the most significant engineering accomplishments in human history, producing science that cannot be obtained any other way. But the achievement exists inside a universe that is structured on scales that make it nearly invisible from any cosmic perspective. The universe contains no mechanism for acknowledging what we have done. There is no system that registers the passage of a human-made object through interstellar space. The distances between things were not arranged to accommodate human ambition, and the farthest thing we have ever sent is, from the perspective of the galaxy, still barely beyond home. The silence out there did not change when Voyager crossed the heliopause in 2012. The interstellar medium did not shift. No response came. No acknowledgement was made from anywhere. The universe is the same size it was before we launched. The distances between things are unchanged. The stars are where they were. The galaxy is doing what the galaxy was doing. And yet the mission has been going for nearly 50 years. And the machines are still moving, and the data is still arriving, and the people at JPL are still listening. And the science being done with the data those two small machines return is contributing to our understanding of the environment between the stars in ways that nothing else could. The horror that the title promises is not in any single fact. It is in what happens when you hold all the facts together simultaneously and look at them without looking away. The machine is moving and will never stop. The power is declining and cannot be restored. The instruments are going dark one by one and cannot be replaced. The golden record is drifting through a silence so complete and so vast that the probability of encounter is vanishingly small. The mission will end and the object will continue, carrying the sounds of a world through interstellar space for billions of years, alone and unreceived. And all of that is true simultaneously. The universe does not acknowledge Voyager's existence. The universe is not indifferent in any cruel or intentional sense. It is simply structured on scales that have nothing to do with us, and Voyager's path, however extraordinary from a human perspective, is a demonstration of that structuring rather than a refutation of it. We have sent something to the stars. We have sent it as fast as we could. And after nearly 50 years of travel, the nearest star is still effectively unreachable on any human timescale. This is what the universe is. This is what it looks like from the inside. This is what the Voyager mission has revealed with more clarity and more specificity than almost anything else we have ever done. There is a way to understand the Voyager mission's relationship to scale that is neither triumphant nor despairing. It is simply descriptive. The machine went as far as the laws of physics and the engineering of the 1970s, and the budget of the time allowed it to go. It went farther than anything has ever gone. It is going further still. The distance it has covered is genuinely extraordinary by any human measure, and it is, by the measure of the universe, almost nothing. Both of those things are true simultaneously. The extraordinariness and the tininess coexist without resolving into a conclusion about human significance or insignificance. The universe does not offer that conclusion. It offers only the distances and the silence and the continued motion of a small machine through an enormous dark. What the Voyager mission reveals about the universe is that the universe is structured in a way that makes it very difficult to leave. Not impossible, the machines did leave the solar system. But difficult in a way that scales with ambition. To reach the nearest star would require not decades but tens of thousands of years at Voyager's speed. To reach the nearest galaxy would require time measured in millions of years at the speed of light. The universe is not built for visiting, it is built for existing in one place for a very long time. We have built one machine that has demonstrated this by almost reaching the edge of our own local neighbourhood after 50 years of effort. The demonstration was worth making. The lesson it teaches about the scale of everything beyond that neighbourhood is the most important thing the mission has revealed. Come back to now, come back to this moment, to this year, to the engineers at JPL who are still pointing antennas at the sky and listening for a signal that arrives after nearly 24 hours of travel, carrying a power 20 billion times weaker than a digital wristwatch, containing data that no other instrument on Earth could receive from any other source. The mission has not ended. Voyager 1's transmitter is still running. The magnetometer is still measuring. The plasma wave subsystem is still listening. The data is still arriving 160 bits per second from 170 astronomical units away, from a place no other human artifact has ever been. Right now, as you finish listening to this, a signal is travelling from Earth toward Voyager 1. It left approximately 23 hours and 32 minutes ago, and it has not yet arrived. It is carrying operational commands to a machine that has been receiving such commands since 1977. The machine will receive it. It will process it. It will continue doing what it has always done, moving outward and listening and sending back whatever it finds. In November of this year, Voyager 1 will cross one light day from Earth, the first human-made object to be this far from home. From that point on, any command will take a full day to arrive. Any response will take a full day to return. The round trip will span 2 calendar days, and it will keep growing every day for the rest of time. The horrifying truth about the Voyager journey is not any single fact. It is the accumulation of all of them together, held at once, without looking away. The distance that grows without stopping. The power that declines without reversing. The instruments going dark one by one, each shut down permanent. Each one a small and irreversible loss in a place that no replacement will ever reach. The golden record moving through interstellar space on a trajectory with no intended destination, carrying sounds no one may ever hear, in a format that will remain intact for longer than the civilization that created it will exist. The mission ending and the object continuing. The silence becoming permanent. The machine still moving in the dark, but there is something else inside all of that. Something that does not cancel the horror, but sits alongside it and refuses to leave. We knew the distances when we launched. We knew the power would decline. We knew the instruments would eventually go dark. Carl Sagan knew that the golden record was going into a silence likely to outlast human civilization, and he assembled it in 6 weeks and put it on the spacecraft and watched it launch. The engineers at JPL know what the power decline means, and they make their careful decisions about 4 watts per year and the sequence of shutdowns, and they continue listening. Because the data keeps arriving, and the science keeps being worth doing, and the connection keeps being worth maintaining. We sent 2 machines out as far as we possibly could, carrying a record of who we were and what we heard and what we found beautiful, into a darkness that may never know we exist. That decision does not make the universe smaller. It does not change the distances or the silence or the mathematics of encounter probability. it does not make us more significant in any calculation the universe would recognize, but it says something about the kind of animal that made it. We are the species that looked at the scale of everything and decided, despite all of it, to introduce ourselves anyway. We decided that silence was not sufficient reason to say nothing. We decided that a civilization capable of reaching interstellar space, however briefly and however small the object it launched, was a civilization worth describing, and so the signal is still travelling, and the machine is still moving, and the universe is still silent. And somewhere out there in the dark, on a gold-plated disc attached to a compact car-sized machine, moving at 61,000 kilometers per hour through interstellar space, is the sound of rain falling on Earth, and a human heartbeat, and music. Good night. The people who will turn off the last instrument have not been born yet, or are children now, or are young adults beginning careers that may bring them to the Voyager mission in the years ahead. They will make the same calculation that their predecessors made before them. What does this instrument still need to tell us compared to what it costs to keep running? And they will reach the same kind of answer, and they will send a command that will take nearly a day to arrive. And they will wait, and they will receive confirmation, and one more window will close, and then there will be the transmitter, and then there will be silence. But the silence will be on our side. The machine will continue. That distinction matters, though it is not clear exactly how or to whom. The mission will end, and the object will not, and those are two different things happening to the same machine, and the difference between them is not small. One of those events is a conclusion of human activity. The other is a continuation of physics that requires nothing from us, and will proceed whether we observe it or not. We have been participants in the Voyager mission only while the signal has been flowing. We were participants at launch and during the planetary flybys, and when the heliosphere was crossed, and when each instrument was shut down, and we will be participants when the last signal arrives. After that, the machine continues without us. It has always been continuing without us in some sense, because the machine has no awareness of our participation, no experience of the relationship, no sense of the significance we have attributed to it. The meaning of the mission has always existed on our side of the signal. The machine has simply been moving. It will keep moving, long after the last person who remembers working on this mission has gone, long after the last person who read about it in a history book has gone, long after the institution that managed it has changed beyond recognition, long after the planet it came from has been consumed by the star it once orbited. The machine will keep moving through a darkness that does not know it is there, carrying the sounds of a world that will long since have ended, toward a destination it was never given.